Right, good afternoon everybody. Look, I'm Doug McConnell from a new company called MyMax Wireless Limited, and I'm not going to talk about cognitive radio. I'll just briefly introduce who MyMax is and go run through a few other things. A little bit about what we do, what our product is, and what our message is. We're a company that actually came out of Tate Electronics Limited. We started off as a research group within Tate Electronics looking at the whole space-time MIMO areas, and decided that it was an opportunity to commercialise the technology, and so as a result of that, decision was made to set it up as a separate company. It's still owned by the same structure that owns Tate Electronics, which is a trust. But it operates independently. So we have very close relationships with Tate, both through they're our contract manufacturer, but also some of the products are supplied via Tate, some of it direct, and we still share the buildings and many of the other services, but we operate independently though. The problem space that we're working in is the spectrum space. The shortage, the finite nature of spectrum. As stated here, it's a valuable resource and it's scarce. We're not making any more of it. We have to use what we've got quite efficiently. So the whole basis of MyMax has been to exploit the spectrum as efficiently as we can. One of the driving factors One of the driving factors in some administrations from a customer perspective is that spectrum is charged on a per bandwidth basis in a number of jurisdictions. I'm not exactly sure what the situation in New Zealand is, and so there's also a benefit to the customer as well for that, cost them less. So our whole goal is to provide spectrally efficient solutions, and particularly focused on the mission critical type solutions. So we're not talking about the Wi-Fi type space or other things where it's shared services. We're talking about where people need licensed channels to give them the control, the surety that their signals in their network will get through and will perform the control or communications that they require. So as I say, we're all about maximising the spectral efficiency. How do we do that? We do that through MIMO. Obviously, as been described before, and I'll talk about a little more, MIMO is a technique that enables you to squeeze a bit more spectrum into, a bit more information into a given amount of spectrum. Just to sort of present it pictorially, looking at traditional narrowband mobile radio, there's the thickness of the pipe, the data pipe you end up with, is just represented here. Traditionally there were very low rate systems using low baud rates for telemetry and other things on radio, narrowband radio channels, mobile radio channels. There have been techniques introduced to expand that capacity up, the middle group there, to bring that up into the sort of tens of kilobits per second. And then finally what we're looking at is really seeing how much we can squeeze into the pipe. So we're talking about a 25 kilohertz channel, and we're pushing through a raw data rate in the order of 320 kilobits per second. And that's without using any compression techniques, and it's full duplex. So that's what we're talking about. So how do we achieve all this? The basic MIMO concept, and somebody put a slide up a bit similar to this before, is that you have a number of transmitters and a number of receivers all sharing the same channel at the same time. So the transmitters all transmit with possibly some coding on the system, the space-time codes that Des referred to, and then you have a bunch of receivers all receiving the same signals, well, versions of the same signals. It turns out that the signals arriving from each of the paths is slightly different. They're not fully correlated, provided certain properties are met, and in practice you can end up getting, for n times transmitters, you can get n independent data streams through the system. You also get some receive diversity benefits as well, and the net effect is a substantial linear increase in capacity with the number of transmitters. Unfortunately, it's not quite as simple as that depending on the environment, because the paths have to have certain properties to preserve the decorrelation between the signals. If they're too correlated, then the information effectively gets lost. But the concept is there. In practice, this one's shown as sort of more than 4x4. Most of the solutions that we're looking at are either 2x4, 2 transmitters, 4 receivers, or 2x2, 2 transmitters, 2 receivers. Embedded in that is a number of techniques. Obviously we get the receive diversity benefit, which gives you obviously better quality signals, better range. We get the direct channel capacity benefit that comes from transmitting the multiple channels on top of each other, and we get a degree of interference cancellation. So that allows us to deal with some paths that we otherwise couldn't use. All that's involved in a fairly intensive digital signal processing path, including some feedback path to keep it all under control. Very briefly, I won't go into this in fine detail, but the block diagram of the system is fairly similar to any other radio system. In practice, it's a software-defined radio, so all of the demodulation process, the modulation processes, the filtering are all largely software-defined. There is a crystal filter in the receiver, but largely it's the actual channel bandwidth is defined in software. This gives us a degree of control over the fine detail of it, as well as providing the ability to tailor it to the particular modulations that we're using. To give you an example of what we get out of that, that's a real picture taken off air of our highest rate modulation. So that is a QAM 256 constellation running in a 25 kilohertz channel. Now you can't really see very well on the slide there, but there are actually 2 different coloured dots there, and the 2 transmissions superimposed on top of each other on the same frequency. You can see a few interesting distortions in the signal. The limiting factor for practical systems is in this band is the phase noise on all your reference oscillators, and that's what causes that slight skewing that you see there on that. So that produces obviously the data rate that we get, and I'll talk about that in a moment. But as I say, you've got 256 constellation points on 2 planes, which gives you the density. In terms of the spectrum, one of the key issues of the whole approach is that we need a very linear transmitter to ensure that we don't get any spectral regrowth. And again, that's a plot of the output, and it is comfortably fitting within the 25 kilohertz link channel mask. That's actually an ETSI European spec mask that's superimposed there in the background. But a lot of effort goes into ensuring that the transmitter is kept linear enough so you don't get spectral regrowth. You can actually just see some very small signs of it at the bottom close into the band.